Hello, fellow science geeks. Without wasting any time, let's get into today's tutorial. So, today, I pose to you this question. A locomotive with a mass of 6.4 times 10 to the 5 kilograms is accelerating at a rate of 0.12 meters per second squared west while pulling a car. The car has a mass of 5.0 times 10 to the 5 kilograms. Assume that there's negligible friction acting on the train. So part A, calculate the net force on the entire train, and part B, determine the magnitude of the tension between the locomotive and the car. So again, really typical Newton's laws and dynamics kind of problem. So, as always, the first thing I like to do is kind of underline, what new numbers and stuff I can find in the question itself. So obviously, the first sentence, I can see the locomotive has a mass of 6.4 times 10 to the 5 kilograms, and it's kilograms, so don't mistake that for grams. And another piece of given information, it's accelerating at 0.12 meters per second squared west. In addition, it's pulling a car, and we're also given the mass of the car, so it's 5.0 times 10 to the 5 kilograms. So, in my opinion, we have all the information needed to continue on with part A of the question. So let's get right into it. So the first thing, obviously, write down your givens. So I'm just gonna write a little G. So those are givens. You know the mass of the locomotive, so I'm just gonna put a little subscript L is 6.4 times 10 to the 5, right? 10 to the 5 kilograms. And again, another given, mass of the car, so M subscript C. It's 5.0 times 10 to the 5. Also, we know there's a given acceleration, so just A, and it's 0.12 meters per second squared, and it's going west. So you have your given set up, and after you're given, just kind of list out your unknown. So just your unknown in this case there is given in part A of the question. So part A is asking you the net force on the entire train. Now, obviously, the important part is that, we're looking for the net force. But in addition, the key word is also the entire train. And this is the key word, as you'll see, when we start subbing in the values, you'll see why you have to take the entire train to put your numbers in. Sorry, I just kind of had like a brain freeze right there. So obviously your unknown is your force, so you're kind of looking for your F net, right? So you don't know what your F net is. So that's your given and your unknown. What else can we write? Well, just by looking at, we have your mass given and you have an acceleration given, and you're looking for F net. Super easy Newton's law problem. So in this case, the equation I would use, so just E for equation, I would use just Newton's F equals ma. Really simple. Now, so this is the basic equation you would use. Just write this down before you forget it on your test or something. But obviously, what you want to do is kind of like write down the right subscripts and everything. So in this case, I'm going to move on to a new page. We are working in the x direction, right? Because it said the train is accelerating towards the west. So just set up your, just say that this is west, and we're just going to say it's positive. For the sake of the question, I mean, usually we set up as east as a positive, but in this case, if it's the train is just moving west, there's no kind of east component to it. So why should we add an extra negative sign? Just define your west as your positive. So the west is a positive. We have our, awesome equation. So F equals ma. Probably the best equation ever in physics. Gets you through a lot of questions. But I'm just gonna, tweak the equation a little bit. So we're kind of looking for the net force, right? So there's two ways you can write net force. Either you can write F net equals, mass times acceleration, and both these ways are correct. I sometimes like to write sum of the forces in the x is equal to mass, and acceleration in the x direction. So both of these things, both of these equations mean the exact same thing. So don't get worried. You can write either or. I like to a lot of the times I like to write sum. So this is just a sigma sign. Like it just means sum of the forces. So it's kind of like a weird kind of E. So that just means sum of the forces in the x component, and so it was just the mass times the acceleration in the x component. This is a good habit to develop if you're going to be dealing with a lot of component problems. So you're going to be dealing with x and y components. So this is just to kind of set it up like this. But again, if you're fine doing it the F net equals ma way, that's absolutely fine as well. So I'm going to continue with this equation. It's just I like to write it this way. So we know that we know the mass of the locomotive and the mass of the car, and we need to find the net force on the entire train. Now, when I was saying the entire train, this is important. The entire train is not just the locomotive, right? The entire train is the locomotive. So I'm just gonna write entire train is the locomotive. I'm just gonna write LOC plus the car, right? So which means, it makes sense. We'd have to add the mass of the car and the mass of the locomotive. So all we have to do is sum of the forces in the x, you can put a little therefore sign here, equals mass of the train, so m of the train, and times ax. Now mass of the train is super easy. We can just kind of like sub in values. So again, this would just mean, I'm just going to rewrite the equation so we don't forget. So mass of the train times acceleration in the x direction. So remember, so this would mean the mass of the car plus the mass of the locomotive, right, times the acceleration in the x direction. And again, we know these numbers, so it's mass of the car was, I think, 5.0 times 10 to the 5 kilograms. Plus mass of the locomotive is 6.4 times 10 to the 5 kilograms. And again, we know the acceleration in the x direction. It's going 0.12 meters per second squared to the west, right? So we have all these values are given, and you can simply plug those into your calculator, and you should get, oh, it's super ugly writing. So 136800 newtons, right? Direction wise, so this is the magnitude. Direction wise, there's only one direction here, and it's west. Now this is absolutely the right answer. All you need to do is you need to go back to your question, and you kind of notice that all these numbers are like just two significant digits, so like 6.4 and like 5.0 and 0.12. So you kind of don't want to leave your answer as this huge ugly number like 136800. So you want to round it off to two significant digits, and the way you can do this is just by putting it into scientific notation. That's the easiest way. So in this case, the final answer should be 1.4, and you got your two significant digits there, and now you have, like, after your 1, you kind of have like 1, 2, 3, 4, 5, so you have like 5 decimal spots more newtons to the west. So that's how you would give your final answer for this question for part A. So you got your acceleration on the net force on the entire train is 1.4 times 10 to the 5 newtons. So there we go, super easy. We got part A figured out. So let's move on to part B. Now, part B is asking determine the magnitude of the tension between the locomotive and the car. Now, obviously, the car and the locomotive are somehow joined together, so we can, again, sketch out a nice quick little diagram, doesn't have to be something too fancy. So you have your locomotive, and you have a car attached to it somehow. It's obviously it's not a rope, or it's, I used to say, like a metal kind of thing, but anyways, it's attached to it. Now anytime two bodies are attached to each other in physics, you gotta assume like, oh, you know, whatever's attaching them together, whatever it's a rope or a string or metal rope or whatever, it's going to have tension in it. So this is our quick little diagram, and you know, you can say this is the locomotive and this is the car. We know that there was like kind of like this was your F net, right? F net in the x direction. So again, quickly define that this is west and it's positive. So this is your this is not a free body diagram. Please don't confuse this as a free body diagram. we're just kind of like drawing the system, if you will. So this is F net, and it's in the west direction. It's obviously not to scale. Now there is so this is the part kind of like that's joining them together, and there's obviously tension in there. Now tension is a very special kind of force. It's as you know, if you have tension in a rope, it only pulls. So tension is only in the kind of like the pulling direction. So when you want to see the tension on this side of the rope, it would be pulling, right? So when you pull on this side, your force would kind of go towards this end. And if you're seeing the tension on this side of the rope, it would be pulling on this side, so it would kind of be going, you know, the other way, so this way. So tension that way is kind of like, you know, we call it the special force. It's a little bit different from the other forces. So tension forces can only pull, you know, so again, from this end you're pulling and you move towards the east direction, and from this end you're pulling, you move towards the west direction. So let's go back to our question, and we want to determine the magnitude of the tension between the locomotive and the car. So in doing this question, why don't we just assume, let's just talk about the car itself. So let's draw a free body diagram of the car. So this is the car, and I know it doesn't look the same as before, but this is the car. So what forces does it have? It's obviously got your normal force, right? And it's got your gravitational force. So these are the two forces you have in the y direction. Also, we can see from the little sketch we did up here that there's also a tension force, and it's pulling towards the west direction. So we've got an Ft right here, and these are all vector quantities, so technically you should kind of have like an arrow on them. But so that's your free body diagram, really simple. And remember, we're only looking at the car. So you guys must be like, oh, why aren't you drawing like the F net on this free body diagram of the car? Well, you know, the F net it's kind of on the entire system. So, but for now we can just, you know, let it be kind of on the locomotive. So the locomotive is providing, or you know, it has a net force on it, so when it's pulling the car with it. But just when we're looking at B, and for the, you know, for convenience, we're just gonna look at the forces acting on only the car itself. So it definitely has tension. We saw from here it's a pulling force. It's pulling on the car, and it's pulling towards the west direction, right? So we can already see that this is in the west. And again, it's got in the y direction, it always has a normal force and the gravitational force. So again, it's super simple, you know, kind of problem. You got your forces, and you have your and you can obviously, you know, kind of set up again. So in the x component, we're going to write the sum of the forces in the x is equal to mass times acceleration in the x, right? So we know that for sure. But so in this time round, we actually know what F net is, right? So this is the F net we found in part A, essentially. And just for the sake of convenience, I'm going to continue this problem in the second part of this video. So please come back.